Thank you, everybody, for joining me today. My name is Rudy Agovic. For those of you that don't know me, I have been consulting in the space of AI and machine learning since 2011. Originally came out of academia. Most recently, I've been helping out businesses with generative AI and helping them to get value out of it. So today, this is my second webinar in my large language series. So obviously, there's been a lot of interest around large language models and how to make them work for businesses. There's so much hype around it, and it's so popular that I don't really even need to talk that much about large language models. Most people already know that they have some issues, including hallucinations, which make them somewhat difficult to apply for some business problems. So if there are use cases where you can live with some level of hallucinations and you can guard against that, then it's great. But the problem is with most businesses, there is not really a huge tolerance for making things up. I will provide an overview for large language models as it pertains to this fusion of large language models and knowledge graphs. And then I will cover knowledge graphs to some extent as well. Then I will go into what I call here the lowest hanging fruit. And so what that really is kind of a walkthrough through a use case that I've been involved in, and it's in essence like a practical guide for something that has worked. That's going to be the lowest hanging fruit, is that use case, and from there we will dive into available methods. Most of that comes from a literature survey that I will share with you. Then we will dive into various approaches that can be used to enhance large language models or enhance knowledge graphs or kind of use them jointly. Now, let's talk about large language models first. And I know we have a pretty nice mix in the audience. We have fairly advanced people in AI and machine learning that know this field very well. We have business leaders, we have even some knowledge engineers and ontology people. So a pretty interesting mix. There's certain things that I'm not really happy with when I look at my LinkedIn feed or how people are talking about large language models. So I'm going to try to provide you a perspective that you might not get elsewhere. When it comes to large language models, this is kind of an overview of everything that has been put out. Well, not everything. Some of the most recent things are not on here, but you will see development started somewhere around 2018. We had BERT that came out, GPT-1, first version of it came out. And then there's been quite a bit of activity. GPT-3 came out in 2020, and it took quite a while until ChatGPT came out, which was sort of the thing that provided all this visibility and attention out there. And then lastly, GPT-4, and now there's been quite a bit of activity within the open source models. Facebook has released Llama 2, which is available for commercial use. So when you look at this picture, you're going to see that it's kind of divided into three categories. One, it says encoder only, encoder decoder, and then decoder only. So I want to kind of cover these three categories a little bit and give you a sense of what those mean and why they're relevant for some of the things that we will be talking about later on. So let me start out by saying a few words about this transformer architecture, which is kind of at the core of all of this development of large language models, because all of them are pretty much based on this architecture, and it's something that was introduced by Google. And as I'm talking about these things, I will try to keep it at a conceptual level so that people that might not be as deep in the field have a chance to kind of follow along. This model is comprised of multiple modules, if you will. One is called an encoder, the other one is called a decoder. So I just want to kind of provide a walkthrough of how that works and what it does. So in essence, what these things are, there are sequence-to-sequence models. So you, as an input, you provide a sequence of words, and they generate a sequence of words as an output. So in this particular example here, I have this question, who is the King of England? And let's assume that goes in as the input. So this encoder box, what that does is it generates a numeric representation of this sentence. You take language and you convert it into something numeric. And when it's in something in a numeric space, now you can do all sorts of mathematical operations on it. And so that's desirable. So that's what the encoder does. It literally takes a whole bunch of words and creates a numeric representation of it. And then the decoder, what that does is it will take, so it has a mechanism in it that's called attention that connects what happens within the encoder with the decoder. And what the decoder does is it will start, and you can't see that because of the video here in the corner, but you will start out with kind of a token, special token called start, and with this input. And what the decoder will do is it will generate the first word. And so the first word would be, let's say the response to this question is, it is Charles. So the first word would be it. And then that word is taken down and appended as, you pretend that it's part of the input into this decoder, and you feed it through the decoder again. And then it will say it is as the next most likely word. And you take the is and you add it to the input and you feed it through the decoder again, and then you will get Charles. So there's two things here to note. One, the generation is happening word by word, and secondly, you are taking the output of this decoder and you keep treating it as an input. And for this reason, this type of model is called autoregressive. You might hear that in the literature. That's what that refers to. So this is sort of an overview of the architecture. We will not go any deeper into it, but I do want to emphasize the nuances between the three categories that we mentioned to begin with. So let's get into that. Let's see here. So one category of models was encoder only. Encoder only does not have that entire decoder piece. It just generates a numeric encoding. And so when you start looking into these models and try to understand, what they're designed for, it turns out that these models, they work very well in this numeric representation. It's also referred to as an embedding. They work very well in creating embeddings that can capture meaning. And so these types of models work very well for tasks that require understanding. So if you look before, there was that model called BERT that was one of the first ones in 2018, 19. And it only has 110 million to 340 million parameters. Now, what if I told you that this model is better in some tasks than GPT-3, which has 175 billion parameters? So that's kind of the point that I'm getting to here, and why I wanted to emphasize this. People are all talking about ChatGPT, about how, basically as if it was the king of all models and there is no more need to look even at anything else. First of all, these models are enormous, and even if you're able to, train them somehow efficiently, when you're doing your inference, you have an enormous model that you need to fire to get to your output. So they come with a cost. And my point here is it's really important to understand what the benefits or what it is that, what the value is that GPT brings to the table, and where it might not be as as notable, that value. And I'm saying this because I'm seeing, first of all, because I'm seeing influencers that might not talking about GPT as if it's the last model we will ever need. So that's not right. And secondly, what I'm seeing is businesses applying GPT for things, for very for things where it shouldn't be applied, just so they could claim that they're doing generative AI. And so if you look at the disadvantages box on this one here, the encoder model is not capable of generating text. So you would not put this into the generative AI column. But if you're doing sentiment analysis and you're using GPT just so you can say you're using GPT, that is not the best thing to do, because this model might actually perform better. And we will get to why that is. There's a reason for it. But that's point one. There is, so this is where you would use encoder-only models, classification and sentiment analysis, and NER stands for named entity recognition. So if within text I have words like customer, product, that I want to classify and basically label as those entities, that's what that is, named entity recognition. All right, so we will get to the next one, which is the encoder-decoder approach. So that is basically, the transformer architecture as it was intended. Now this combines both the decoder and encoder and gets you sort of the best of the two worlds. It is able to generate text. So if you're using one, you could claim you're doing generative AI. These models tend to be more versatile than GPT type models, in that they could be applied to different types of data and different types of applications. And they tend to do really well for specific tasks like language translation and text summarization. And so if you look down, I have a list of these models that are taken from the chart. There is BART T5 and then FLAN T5. So FLAN T5 tends to outperform GPT-3 on some tasks like language translation, simply because this architecture is more suited for it. So the point here being, again, depending on what your use case is, you need to understand what the benefits are, what the weaknesses and strengths are of these different architectures before just blindly going to GPT and the biggest models. And now we're going to get to the decoder-only models. That's the third one. Decoder-only models, that's where GPT falls under, and Llama 2, and like all of these that are discussed. There is a property that they have that makes them more scalable in their training, and that is the reason why with these models you can go to 100 billion parameters and it's computable. And we will get to that reason on the next slide. But the advantage of these decoder-only models is that they can generate fluent and coherent language, as most people have witnessed. They're good at text generation and summarization and having a dialogue. But they're not as efficient in encoding inputs into numeric representations. So basically what that means is if you have some kind of a classification task, something where you just want to get the embeddings and then work with them, you want to really closely take a look at the other models. The reason I'm telling you this is because today's topic is the fusion of knowledge graphs and large language models. And there's if you fuse those two, there is a high likelihood you will end up working in some numeric space. And so this is an important consideration. Now, moving on, the next part I want to address is the attention mechanism. I mentioned this. All of these transformer models have some form of attention mechanism. It is the means by which you're relating words, really. And the way GPT works is sort of this red side. It's called causal attention mechanism. And the reason for that is because when you're looking at the word king, it will only be relating king to whatever came before it. It will not be relating it to the words after it. The reason for that is because this is a decoder-only model that generates things a word at a time. So you can't be relating things to something that's in the future and that has not been generated yet. So that's by design. And the reason that it is simplified like this and that you only have the decoder is what makes GPT type architectures, these decoder only architectures with the causal attention mechanism, more scalable. And once they do get to about 100 billion parameters, there's certain properties that become more pronounced, like being able to do a few shot prediction type tasks. And what that means is I could just ask the model to do something without giving it a lot of examples, and it does it for me. It gets better at that at the larger size, and also it's more capable of maintaining a chain of thought. What that means is you're having a conversation with it, that it's able to refer to what you discussed previously, and it kind of seems like you're having a natural conversation with it. So that attention mechanism plays a role in that. There is an alternate attention mechanism which is called bidirectional, and here when you're looking at the word king, you're relating it to everything that came before it and everything that comes after it. So Bert, Ernie, and Bart are models like that. And when you deal with problems where the context of the words is important, like sentiment analysis, this is the reason why these models will perform better, is because they're better at capturing the contextual meaning within the sentence by design. So eventually, once we get to, I don't know, GPT 5 or 6, maybe at some point those will start surpassing BERT in performance and sentiment analysis. But like even with this huge difference in size, it's still the model to go with, and it's much more efficient. Now, there's one of the last things I wanted to emphasize on large language models before we move on. There's a paper which I shared in my last webinar as well. It's from NIPS in 2022, where basically what I did in this paper is try to understand how large language models are maintaining facts. So they looked at certain facts. I think in this case it was the Space Needle is in downtown Seattle or something like that. And they tried to see if they could locate in the neural network, where is that being stored and how is it being stored? I mean, it's not, it's conceivable that information might be, in multiple places, like you have 100 billion weights, that's enormous. So what they found in this study is that they could locate the activation functions that were responsible for this fact. And they devised a methodology that you could use to kind of surgically modify the fact in the large language model. The implication of this is that you can think of large language models as kind of a knowledge base. It goes out and it's fed through all this data on the internet, and then through all these prompt response pairs that OpenAI feeds it, or with the open source model, whoever. And all of that knowledge is internalized. And the other thing to note is there are much smaller models that are able to have, natural sounding conversations, which means that you don't really need 100 billion parameters to enable, conversation in English that's fluent. So basically, the implication of all of this is that most of those 100 billion parameters are actually utilized to store information. and it is stored in a way that is not really very reliable. So if I'm a business and like I have a lot of facts and knowledge about my business, the question is, does it make sense for me to infuse this knowledge into a large language model to then like basically have things that I know to be true or false no longer be reliably true or false? So that's really kind of the dilemma with the large language models. The way facts are being stored is up to some kind of gradient descent approach, and how it ends up setting weights. And maybe the next time around it's trained, the weights might be set slightly differently. So it's not really, it's a complete black box with no transparency around how knowledge is stored or how it's doing its reasoning. And that's problematic when you have, let's say I have documents that specify information about regulation, and I have a client that wants to know this information. I can feed it all these documents, but I have no control what it's going to pick up. It might pick up just the right things that I need, but it might be picking up like something completely different. And even after training the model, you have no guarantees that it will end up picking up the things that you care about, which is really why we're talking about knowledge graphs today, to see if we can kind of do something about that. Looking at large language models, we have kind of some advantages and disadvantages. The advantages are that it has vast amounts of knowledge. Excuse me. It's quite general. I mentioned the few-shot learning, so I can just tell it, write me a poem about cheese, and it will do that, with no examples. And then this idea of, that it has some limited degree of reasoning capability and the ability to maintain a chain of thought. So that's kind of what impressed people. But on the downside, it does create hallucinations. It's unreliable, and as I already mentioned, both in terms of how it stores data and reasoning, and it lacks domain-specific knowledge. So if I'm a business and I have my own data, well, somehow I need to get it in there. So that kind of sums up large language models. Now we're going to dive into knowledge graphs a little bit. So knowledge graphs. Now, I don't know to what extent the audience is familiar with them, so I'll just give a brief background on them. Knowledge graphs are basically represented by a collection of entities, which in the knowledge graph are represented by nodes. So we have here, you can see Apple Watch, Apple, and Band. Band is a product, and then Apple Watch is another product, and then Apple is the company. And then we have relationships which are represented by edges. And here, Band is an accessory of the Apple Watch, and then Apple Watch is made by Apple. So that would be one example of how entities and relationships are being stored in a knowledge graph. Now, there are different ways how you can basically implement a knowledge graph. There is one representation called RDF, where it's basically triplets of subject, predicate, object. So here, Band would be subject, the relationship is a predicate, and this is an object. Apple Watch is an object. And the other way of articulating them is something called property graphs, which is what Neo4j implements. It's a bit more loose way of using knowledge graphs. I will not go into the details of these two. I will add a reference eventually in the slides when I share them to various different knowledge graph technologies, so you can take a look. One other thing I would note, because we have knowledge engineers and ontology people in the audience, an ontology you can think of as a formal representation of knowledge. And when I mean formal, I mean it's really like articulating every aspect. There's very specific rules of what an ontology must have, and you must define that. And if you do that, it's basically like if I have a customer what does the customer have, what kinds of properties the customer has, what kind of relationships the customer can have. So it dictates the schema of the graph, but it also dictates how a knowledge graph is generated. And one important thing I want to note is that not every graph model, or like, I don't know if you're going to call them knowledge graphs, necessarily has to have a formal ontology. Sometimes you just want to represent your data as a graph, and you don't have formalized rules about how that must happen. So the reason I'm mentioning this is just to emphasize the connection between knowledge graphs and AI. So people are talking about AI as if it's something that just started with GPT. It is a field that has been around since the 50s, and ontologies have played an important part in that. So they have been utilized within AI since the 80s. And one important thing I want to also add, when you have a formal definition of ontologies, it has things in it like concepts, properties, relationships, and another thing called axioms, which is basically a set of rules that dictate how you might create additional relationships. So it'd be something like, if customer buys product, then customer owns product. And that would be, basically a rule that would tell you that, there is a relationship here now. So when they say you could use knowledge graphs for reasoning, that's what that's referring to. It's this more formal description, a bit more formal definition of an ontology that sits and dictates the structure of the knowledge graph. If you have that, then with the ontology and reasoning, like logic reasoning, or like any kind of computer-based reasoning, you can then derive knowledge. And so this is one thing that I say is a positive with knowledge graphs, and that's what that refers to. And I just want to emphasize, when you talk about knowledge graphs, this is not something that's new to the field of AI, at least from an ontology's perspective. So how are knowledge graphs used in business? With the rise of something called native graph databases like Neo4j, TigerGraph, Stardog, graph databases and the ability to maintain enterprise knowledge graphs at scale became more available, so that businesses now can have billions of nodes in a knowledge graph, in an enterprise knowledge graph. And what this native part means is that these kinds of databases, so if you have a path, they literally store it as a path, and they allow you to traverse that path very efficiently. Whereas if you had that data in a relational database, traversing a path would amount to a whole bunch of joins. And if your table has millions of records, then you're doing a join, just to get 7 hops ahead, you have to do a join 7 times over, with the same table. And it's just, it was not designed for that purpose. SQL databases are great for what they're used, but for path-based data, not so much. Knowledge graphs, what they do is they allow you the ability to manage enterprise knowledge in a transparent fashion. So one example would be managing products and their relationships, like an ontology of, okay, we have the TV here that we sell, and then there's a wall mount, and the wall mount is compatible with this TV, and the TV belongs to the TV category. So very frequently businesses completely see the picture that it would be necessary to maintain these kinds of relationships. And why? Because it ends up being difficult, because that type of knowledge evolves over time, and you need something that allows you to evolve the knowledge. And doing that with just a typical relational database is kind of cumbersome. Now, another way in which enterprises can use knowledge graphs, which people don't necessarily think about immediately, is to capture journeys. So a customer has a journey, a sales cycle is a journey, a product goes through a life cycle. So when you think about events that happen, then basically there's lots of paths that happen in enterprise data. And if you sort of start connecting those paths, then suddenly a graph emerges. So, sales rep and the marketing journey might be connected to the sales journey through a sales rep interaction. And so suddenly the dots get connected. This is an aspect where, even without a formal ontology, businesses can drive a lot of value from knowledge graphs. The other thing that's important to note is when you want to build a knowledge graph, you don't just take your data and dump it into a knowledge graph. First of all, you need to think about what data is important to me. Like, well, not what data, but what kinds of things do I want to know from my data? So that's the first step, is understanding what questions do I want to be able to answer. Once you have established that, you think about, well, what data do I need to answer those questions? And then a third step is where you have a knowledge engineer basically figure out how to organize the knowledge, how to connect the dots with the data that we have so that we can efficiently answer the questions that we want to answer. And so what I really like about this is that, one, it forces businesses to think about data strategy, whether they like it or not. Because once we, talk to them about this, they realize, oh, but we're not there. And you really need to think about how you want to be using your data before you start implementing it and dumping into some, a database. So that I like, because it gets back to the question of data strategy, which is lacking in a lot of companies. And it's really important to deliver on AI, and specifically to deliver on large language models. And the other aspect of this that's really valuable is, if you think when you're doing AI or machine learning, you're going to eventually you start doing feature engineering. You get to a point where you need to figure out what matters, what knowledge matters, so that then I can start piecing together features that might be valuable. And so, like, I'm emphasizing that because here, if you've gone through this effort, you've kind of already put in thought into what knowledge matters. And so you've created a foundation to start leveraging AI. And from an LLM perspective, it's something that you can derive a data set from. So learning over graphs, I just want to quickly mention this if you guys are not familiar with it, because this will come up. So just like there are transformer models for sequences of words, there are extensions of transformer models to graphs, where you have basically a node, and then there's an attention mechanism that relates the node to its neighboring nodes. There are also convolutional networks, they're called graph neural networks, that exploit a similar principle. They're based on convolutions, but they're looking at the neighborhood. And then lastly, there's also temporal graph neural networks, which means if I have a structure that changes over time and I want to model that. So there are neural networks that are able to do this. And if we want to start fusing things, that can be important to know. So I would advise you to sort of read up a little bit on these. Moving on. We've already talked about this, but advantages of knowledge graphs is that they're interpretable. They do store domain-specific knowledge. They have the ability, with them, you have the ability to manage your knowledge and evolve it over time. And if you've set it up properly, the knowledge in it will be accurate. Now, knowledge graphs are by no means perfect. They have their issues as well. And one of the disadvantages is that they're lacking any kind of language understanding capabilities. So if within my knowledge graph I've received an email, now that email might say something, hey, Rudy, I will accept the deal, sign me up tomorrow. I would love to infuse that knowledge into my knowledge graph, but somehow I need to extract it from that email. So by itself, a knowledge graph doesn't have that ability. And it also has issues with unseen facts. Like, I've engineered the graph, but then there might be gaps in my knowledge. And how do I fill those gaps? How do I identify that I even have gaps in my knowledge? So those are issues that knowledge graphs can't handle very well. But as you can imagine, large language models would be really nice for those types of issues. So what this boils down to, if you compare the advantages and disadvantages of both, is that these two technologies complement each other well. They kind of help with the weaknesses that the other has. So now what I'm going to do is I will walk you through this practical use case. So this is based on simple example that we have gone through. And if you're interested in interfacing if you're interested in using large language models to either interface with a database or a graph database, this will be useful to you. So let's dive in. So let's assume that we have an organization where we have Salesforce data from a CRM. We have point of sale transactions, so we know when a purchase happened. We have e-commerce clickstream data, and then we have marketing campaign data from Marketo. And there's an app with this particular organization called Modus. It's a sales enablement app, and what that does is it manages marketing assets. So if let's say a video or a picture is shown to a contact in the CRM, it basically helps the sales reps manage those assets and track them on how they're being opened and whatnot, so that you could take action. So these are very typical sources of data from enterprise. We started out by getting a list of questions that were interesting to the stakeholders, and our first step was to engineer a knowledge graph that would capture this data with those questions in mind that we could answer. So the requirement here was we wanted to, or they wanted rather, to build, provide a capability to them, to the stakeholders, to obtain sales enablement insights from this data. And well, with the stakeholders, there's not a whole lot of patience. So the tolerance for the inability to retrieve data is not very high. So with that, I don't mean that necessarily that the model is hallucinating, but you ask for something and it's just not constructing, retrieving the data properly. And the last one would be a kind of a zero tolerance for hallucinations, because stakeholders don't like to make their decisions based on hallucinated data. So to give you some examples of what we're looking after is that a lot of these leaders would like to be able to ask things like, which sales rep had the shortest sales cycle over the last 3 months? Or what is the most likely path to purchase for our lawn care product or whatever product you may consider? So those would be the type of questions that we needed to, basically answer. And specifically, the request here was whether we could use generative AI or large language models to address this. So our initial goal with this problem was to identify what is the least amount of effort we could do to get this to work. So the first approach was to say, okay, let's take GPT 3.5 Turbo, which is the most recent version, and GPT-4. We've created the knowledge graph. Let's describe the knowledge graph in terms of create statements using, so Neo4j has this query language called Cypher, and it's basically kind of pretty simple to use. A lot of different graph database products implement this language. So create statements in that language would look something like this, what you can see on the slide here. And we would, like the ontology internally would have something like an account. An account is related to a contact in Salesforce, and a contact is tied to an opportunity. An opportunity goes through opportunity stages. We give the knowledge graph description to the model, and we ask it, well, act as our assistant now, start answering questions. So this is sort of the first step. If you do that, what you're going to find, in this case, the knowledge graph is pretty, decent size. You have all these relationships from Salesforce, from marketing, from the website even. And that's quite a few entities and relationships that are possible. And I'm not, given the model anything other than that structure. And then I ask it, well, here's the question, who is the most successful sales rep, or things like that. And what you find is that it starts hallucinating properties, like what aspects of if I'm saying most successful sales rep, it might attach some kind of a numeric value to a product that I don't even have to compute how much that sales rep has sold. Or it invents relationships, entities, and properties. Most of the time, not all at the same time, but it does that. And it doesn't do it with every question. It's just that maybe we have one simple question and actually gets it right. But then like as you start playing with it, you see, oh, this is bad. So yeah, and we've done this with databases as well. If you just give the database structure, this is kind of what starts happening. So the advice here is, hone in on those problems that you see. So you give it a question and it's coming back with invented fields. So in this case, what we're trying to build here is a model that, given an English sentence, gives us back a query into Neo4j. So that's what we're trying to do. So we give it a question and it gives us back a query, and we're seeing, well, it has a whole bunch of made up stuff in it. Now, if you were dealing with a database that's not a graph database, you would be getting back a SQL query, but I can tell you already, you would be running into the same types of issues. So what you want to do is you start generating prompt response pairs, meaning I have a question like, who's the most successful sales rep? And then I create the query that will answer that question. And so as I'm hitting things that it's inventing and not able to respond to, I just keep creating the proper response, and then I take those prompt response pairs and I add them to the context. So now I have the structure of the whole graph and a whole bunch of training data that I've just given it. And so when you do that, you're going to start seeing it perform much better. It starts generating really good looking queries, but it's still from time to time makes stuff up, especially if you try something that you haven't even considered in your training data. Now, one thing that helps here, if you want to get it to perform better, is these models have a parameter called temperature, which indicates how probabilistic the model is. If you dial it down, it becomes more deterministic. If you dial it up, it's more probabilistic. So in that decoder model, the GPTs, the decoder, the last step is basically what it does is it has a likelihood of over all the possible words in the dictionary, and then you are sampling a word from that, the most likely word. And so that's where the probabilistic aspect of this comes into play, and you have some lever to control that. So basically what this means, in other words, is you're telling the model to be less creative. And so by dialing down the temperature, it helps for it to not invent as many fields and things of that nature. So that's one problem you're going to run into. If you follow these steps, you're going to already see, decent performing chatbot that keeps generating queries for you. And what in essence, what we have decided to do here is we have decided to use the coding capabilities of the model to retrieve data from, or knowledge from, the knowledge graph. And we're not relying on the knowledge of the large language model at all. So that, what it does is basically allows us to, fight the hallucinations. Because now the biggest kind of error that can happen is that maybe it creates a query that cannot be executed. Maybe it misforms a query. Now, validating a query is a whole lot easier than validating, anything that's generic. So that's why this whole hallucination problem, like our requirement here was no hallucinations at all and very few mistakes, if any. And so that's kind of the approach we've taken here. So, but if you try to refine this further, you're going to find another problem. And I'm telling you this because there are packages like LangChain that try to give some of these capabilities. They're not as great with KnowledgeGraphs. They have some more extensive capabilities on the SQL side. But a lot of people have tried that, find that it's not overly useful to get into the weeds. Like, you can get going, but then you find these kinds of issues. So the next thing, it's a big thing that happens, is you have business data that's normalized. So if I have sales opportunities, I have defined exactly which opportunity steps I have. If I have a product catalog, I have very specific names for my products, and those products have very specific properties. Now, the thing is that when the user asks for things, they might not have the normalizations memorized in their head. They might not know how to refer to things. So there's a disconnect, and that disconnect may be smaller if it's an internal use case, because if you have a sales rep, he might know exactly what he's looking for in the data. I don't know, but some sales reps may not. But if you have an application that's client facing, then it's even worse, because you can't assume that your client will use your internal terminology to articulate things. So this is the next problem you're hitting, is the model is able to generate queries, but it may, infuse conditions and things into these queries that it doesn't know don't exist. So if, let's say, the user specifies, I'm looking for the lawnmower 3000X, it may just put that lawnmower 3000X right into the query, and that product might be called slightly differently. And so that's the issue. There's an alignment problem. There's two things you can do to fight this. One is to add more examples to basically address some of these issues. But the problem is, it's really difficult to capture all of those issues, because, well, users can just come up with, if you've ever built software and give it to be tested, that you just can't anticipate all the different ways that they might ask for things. So here is a problem that so the next wall that you hit is, when you do this, now you're going to start running out of examples. So ChatGPT or GPT 3.5 has different versions. There's like a 4,000 window size, 8,000 window size, I think 16,000 and 32,000, if I remember correctly. Well, basically what it means is, the window size is expressed in terms of tokens. Tokens kind of loosely translate to words. Not exactly. 1,000 tokens is maybe about 700 or 800 words. So what that means is, if I have created so far 100 or 150 examples to articulate what's right and how the model should respond, I'm going to start hitting that limit eventually. That's a limitation. And it's particular limitation if you are not a huge fan of using OpenAI, and you really want to use an open source model that you can own internally. Because what you will find is that a lot of the top models there, like Llama 2, like Falcon 40 billion, they only have 2,000 tokens window size. So that means you're not going to be able to give it that much training data in terms of a prompt. So at this stage, if you want to move forward, you're likely going to be forced to start fine-tuning these models. So with fine-tuning, you can basically have thousands, hundreds of thousands of examples that you could feed into it. And not only that, with the fine-tuning, you can construct. So you can construct, with the fine-tuning, you can construct also prompt response pairs that will capture the variability in your data. So let's say if I have a field that's opportunity stage, if I do it properly, I can infuse that knowledge into the model, that it has more of a sense for what constitutes an opportunity stage, or what types of products exist. Because if the model is aware of it, then it can use its natural language capabilities to let the user know, look, we don't have that product. Did you mean this? Or could you please reformulate your question? I'm not sure what you're asking for. So that's kind of, and this is where things get a bit more involved, because now you have to fine tune a model. Now, places like OpenAI, they, you don't really have to deal a lot with the infrastructure to fine tune it. Where you have to invest the time is to come up with the data set. And the data set is something that, if you are contemplating to use large language models on your own data, it's really something that you could be working on right now, because these models are getting better. There's going to be more of them out there. And the one thing that will make a difference is whether you have organized your data the right way and whether you have a data strategy in place. Now, if you have a use case in mind and you don't feel like working on developing models, it would not be a wasted effort to start preparing training data. So that means working on those prompt response pairs for the use case that you're interested in. So in step 1, we utilized a large language model to translate a question to a Cypher query. The Cypher query was then executed against a knowledge graph to obtain a response to the question or the original query. Now, in step 2, we would like to summarize this response back to the user. So we use the large language model to accomplish that. We provide the original question along with the result as context, and then ask the model to articulate a response. So for this particular task, we found that the model was doing a pretty good job. It was not necessary to provide example prompt response pairs or to train the model in any way. Step 3 here, so we went through generating the query, summarizing the response, and now we're asking it to visualize the response. And we're doing that by asking it to generate a JSON file that can be used as a configuration for a visualization in some JavaScript library. So that way, we're not asking it to generate visualization logic necessarily, but more of a definition file, if you will. For this step 3, it did a decent job without any direction, but it would have the tendency to always pick a bar chart or stick to one type of visualization. We ended up having to give it a bit more instruction here, not overly too much, like 10, 20 different examples, just to have, just to give it more variability, and with very few examples, the model was able to accomplish this. So with this particular use case, so this is, as I mentioned, very simple but effective. We were able to remove hallucinations basically, because we're not relying on the knowledge large language model at all. We were able, through constructing a training set and constructing and fine-tuning and going through all these steps to get the accuracy to an acceptable level. And with the knowledge graph in place, we have now knowledge that's transparent and manageable. So we were able to address all of these issues. Accuracy is not perfect. There's still things that you can come up with, but with the proper guardrails in place, at least you can let the user know things like, oh, I'm not able to answer that question, or could you please reformulate? So you can catch a lot of things that way, and then the things that come back uncaught then end up being a small fraction. Now, all of this comes at a cost. We have a particular set of requirements, and a lot of businesses would be fine with these kinds of requirements, I would say. But it comes at a cost in that here the large language model is utilized only for its ability to create code, to summarize a response, and generate the visualization. The reasoning capabilities of the large language model are not utilized at all, or so the more generic knowledge is not utilized either. So, that can be limiting to some. to us, this has been kind of like a very extreme cut where we said, okay, we don't like dealing with hallucinations is not, and especially if your tolerance is 0, we have to take some drastic, steps, and that's what we did. And so, like if you look at LangChain, you're not going to see this sort of walkthrough. So I hope that this is useful to some of you out there that are contemplating to play with this. My point with this is there is a low-hanging fruit that you can implement, and get a use case going without without having to spend enormous amount of resources to get it up and going. So, but to some organizations this is not enough. So when we are talking about fusing large language models and knowledge graphs, what would be really interesting is if we could fuse the reasoning capabilities as well, and basically fuse them at sort of a different level than what we're doing here. Here, we're just, addressing a particular business need. So that's kind of what this last segment of this presentation is about. We take a look at what's available out there. There is a literature survey called Unifying Knowledge Graphs and Large Language Models, a roadmap. I'm sharing a reference to it. A lot of the overview that follows is from that literature survey. A lot of the graphics I'm using are also from there. Now, the first way of thinking about enhancements is to, basically have large language models which are enhanced by knowledge graphs. And so the reason why you would want to do that is basically to reduce hallucinations, enhance reasoning capabilities, and have better interpretability. Note that we're saying here reduce hallucinations, not necessarily eliminate them. So that would be why you want to do that. Now, if you think about the various methods that you could use to enhance large language models with knowledge graphs, you can kind of roughly bucket them into 3 categories. One category would be enhanced pre-training approaches. So this would be basically modifying the objective function of the large language model, or adding the knowledge graph information as input, or fusing the knowledge graph in some way while the large language model is being trained. Now, the issue here is that knowledge evolves, it changes. So these enhanced pre-training methods, always have to do some amount of training. Some cases you have to train the model from scratch, which is very costly, and you can only do that with very small models. Then there are other approaches that will work with just fine-tuning. So there are distinctions there, but you do need to do some kind of tuning or pre-training, basically. And the downside of this enhanced pre-training is that, knowledge evolves. And as knowledge evolves, you basically are forced to retrain every single time. And so, you have to commit those resources over and over again. The next bucket is called enhanced inference. Now, because of this issue that knowledge evolves, with enhanced inference, the idea would be to keep the knowledge space separate from the text space, and to only combine them when you get to the point of inference, of making some kind of predictions, or generating text. So that's the idea with enhanced inference. And then the last one would be providing enhanced interpretability through the knowledge graph. Because if you have fused the large language model and the knowledge graph is sort of the interpretable piece that you can maybe use as a lens into what the large language model might or might not do. So roughly, these are kind of 3 categories when it comes to enhancing large language models with knowledge graphs. Moving forward, I will now go through a couple of example approaches for each of these. I will not go into the gory details of them, nor do I have the time for it, but I will sort of touch upon some of them. So there is a model called Ernie, was proposed in 2019 by Baidu. And what that does is it basically, it runs a large language model on one side and creates sort of the encoding, and then it uses the knowledge graph and creates an encoding from that. But then if I have a sentence like, "Who is the King of England?" it will try to find the corresponding entities in the knowledge graph. So is there an entity for king? Is there an entity for England? And so what it then does internally, it will get the encoding of the entity king, the entity England, and then it will combine the representation of the text-based encoding with the encoding that comes from the knowledge graph. And remember, we mentioned about knowledge graphs that there are neural networks that can be applied to them. There are transformer extensions to the transformer architecture that work with knowledge graphs. So, and also this is kind of the point where I want to emphasize the reason why I was talking about BERT and the distinction between models that create embeddings versus those that generate text. Because in this case, the large language model that is used is BERT, and you could go and say, "Oh, Rudy, I mean, are you like in the Stone Ages BERT? I mean, 2018?" Well, just so happens that this actually makes a lot of sense, because what's happening here is not a generative model. This model is trying to create a combined representation that you can then use for some kind of a task like classification or whatnot. And so BERT in this case does make sense because well, it's actually better than, well, GPT-3, for instance, in creating contextually aware embeddings. So that's one example of how that can be accomplished. Now, when you look at an example like this, okay, so now we have fused the knowledge from the knowledge graph and from the language model. And you could plug in a different language model in here. But this helps guide the large language model, but it doesn't dictate to the large language model to not hallucinate. It doesn't remove hallucination, and it still does not provide you any guarantees that the knowledge that's in the knowledge graph will always be reflected in the outputs, because you're just fusing them in some fashion, and there isn't a knob to say, okay, fuse it, but please always respect the knowledge that we have in the knowledge graph. So there is a lot of approaches in literature like this. This fusion of knowledge graphs and large language model is an active area of research. So when you see these, you're going to find that some of them are in real use, and some of them are just sort of within the research realm. This particular one is actually in real use, or was. I don't know if they're still using it. They have multiple versions of it, but Baidu used this, internally. And there's Ernie 2.0 and Ernie 3.0, and they've created chatbots off of that and actually utilize these models in production. So that's one that actually is in use, even though it's not perfect, but it's better than just letting a large language model loose with no knowledge graph guardrails. Moving on. So this would be another example, an approach called Kayla from 2022. So what happens here is, if you take a look at it, this is developed by the Allen Institute for AI. Again, it utilizes BERT. Well, what it does is, what they're saying here is even though this is enhanced pre-training, this doesn't require retraining the whole language model. Instead, you go and train the language model, and then you do this as an enhancement in the fine-tuning step. So what they do is, let's say you have a sentence like, "Who is the King of England?" It will grab any token that has a corresponding entity in the knowledge graph, like king might have an entity, and then it will take the embedding of king from the knowledge graph, and it will take the embedding that is there from the large language model, and it will then nudge or move the embedding from the large language model to be closer in the feature space to what the knowledge graph is saying. So, and that would be for those entities that have for the words that have a corresponding entity in the knowledge graph. So that's actually, conceptually, this is not very complicated to understand. So, like knowledge graph is giving you one embedding, one representation, large language model is giving you another. Wherever you have entities, you just kind of move the large language representation closer to what the knowledge graph is saying. Moving on, that's example number 2. Example number 3. So this one is called Joint LK, also 2022. And we'll see there's sort of a recurring theme. We're getting back to BERT, which I hope now makes sense of us talking about it, but this is based on Roberta, a variant of BERT. And what happens here is your question answer type of scenario where the input is a question along with a set of choices that you can make. And the objective of the model is to provide, it's like multiple choice. The model is supposed to pick the right choice. And so you have the language model, you have the inputs that's text-based, and then there's a subgraph that relates to the question. So here, what they basically introduce is a module for joint reasoning. So it takes the embedding from the graph, it takes the embedding from text, and it tries to relate them through an attention mechanism. And then based on that, it then generates a score for each one of the choices. And so the benefit of this, because this is what they call enhanced inference, and with they, I mean the folks in the literature survey, because the benefit of this is you don't really have to touch the large language model. You don't have to touch the graph encoder. So the only thing you have to train is your joint reasoning module. So that's the benefit of it. If you already have the graph encoder in place, if you don't, then you train that as well. But the benefit obviously is, if you are dealing with GPT, which is an enormous model, you do not have to, retrain that. You don't have to mess with it. You just focus on the reasoning aspect that's relevant for you. So that's another one that's more recent. Let's move on. There is one called RAG from 2020. RAG stands for Retrieval Augmented Generation. Now, retrieval augmented generation is what LangChain provides, or you go in, you retrieve, so you start out with a query, you go out to your database or knowledge graph, and you retrieve similar documents using kind of a query type search, like from the old days, that may be based on an inner product, like Google might be doing. And a lot of the times, these sort of retrieval augmented generation is also tied to a vector database, or it allows you to do this matching more efficiently. And then you get a collection of documents that you deem to be relevant, and you put that into the context of the model in the hopes that now you will have better context. Most people that try this in practice for production use found that it's not really overly reliable, because, well, you are getting more relevant documents, but you're not addressing hallucination necessarily. You have no guarantee that the model is going to actually leverage the context that you're giving it. Like I might be asking it for the model for my refrigerator filter, and I give it a bunch of manuals in the context, and then it tells me, the filter for a whole different brand that I didn't ask about, because you're not curtailing the language model to not leverage its own language knowledge. So here, it can help if you fine-tune the model in addition. But I wanted to say this approach is not the same that LangChain utilizes. What they've done here is basically they have the knowledge graph, and then they have created a module, like an encoder that encodes the query that is supposed to go grab things from the knowledge graph. So you're trying to learn what that query should be. And once you extract the information, you pass them along to the large language model, and you then pass along the question as well. In this case, which country is Obama from? And it got various facts about Obama, and then with these two things combined, the large language model can use its reasoning capabilities to say United States, because the answer is right there. But what this does is it actually combining the language model with this query retrieval and jointly doing backpropagation, meaning it's jointly learning how to do those things. So that's what makes this different from what long chain does. So it's just one more example for enhanced inference. Let's see. There is one of the buckets was enhanced interpretability. I will say that like this illustration here just kind of shows how you can leverage a knowledge graph for that. So if you have a model where a knowledge graph is fused with a large language model, then you could go into the knowledge graph and you could look at questions that you can extract from it and then see what the large language model tells you. And so basically, if the large language model adheres to that, then the knowledge graph is giving you interpretability. You know what the answers are going to be. And then if the large language model is off, you're going to know that it's off in certain areas because you can test it out. You can analyze the performance of the large language model. So that's how you can actively use, in these kinds of instances, you can actively use the knowledge graph to probe and analyze what the large language model would do. And this isn't like a specific approach. Like these guys in the literature survey, they created these 3 buckets, but they're not disjoint. Like there are approaches that fit into multiple buckets. And so some of the methods that we talked about already that fuse the two, could be used in this way. Moving on. So we're getting now to the second, subtopic, which is knowledge graphs that are enhanced by large language models. And here, and we're coming, getting closer to the end of the presentation, so bear with me. There are multiple things where knowledge graphs can help, large language models can help. One would be completion task. So this is like if I have missing edges or nodes in my knowledge graph, I can talk to the language model and use its reasoning capabilities and inference capabilities to infer what those missing edges or nodes should be or might be. The other use is in building a knowledge graph from the knowledge that the large language model has. So large language model has vast amounts of knowledge. You could start probing it and sort of in the background start building entities and edges and like a graph that represents the knowledge that the LLM has. Some other types of things where a large language model can be helpful is question answering, creating graph embeddings that are enhanced by large language model embeddings. So combining those 2 embeddings so that if you're looking at a neighborhood in a graph and you're doing some kind of learning on top of the graph, now you have the ability to also, if I have emails that are tied to this or any kind of text data, I can enhance the representation of that node to incorporate that. And then lastly, there's a task that is frequently done within knowledge graphs, which is get like a text representation of what the knowledge graph is saying. And obviously, large language models could be used for this as well. I will try to go through these quickly. These are just some examples of what we have discussed. Here we have a sentence like Joe Biden was born in Pennsylvania. He serves as the 46th president of the United States. And you can see there is some action happening here. There is named entity recognition, entity typing like politician, country, state, entity linking, which is like these links, and then I'm unable to read coherence resolution and relation extraction, I believe is what it says. It's tiny on my screen. So one of the things you're going to notice as you start reviewing the literature on this, that a lot of these are language understanding tasks, not language generation tasks. So if you look at this and you're given a sentence, you might be better off to use things like BERT that has that bidirectional attention mechanism, because it's better able to capture the context. Now, if you're interested in extracting knowledge from the large language model, that's a different story. Then you want to go to GPT-4, GPT-3 to kind of get knowledge out of it that you might not have otherwise. So that's kind of what you would use to assess which one to go with. So knowledge graph to text. This is a fairly simple one. Don't really need to go into detail, but basically there is a way that you can just express the relationships and nodes in a sentence. In essence, it's called graph linearization, where you're just expressing that. And then if you give that text to the large language model, it's going to be able to pick up things from it. And here it generates a text description of what the knowledge graph contains. That's a pretty vanilla type of task for a large language model. Doesn't necessarily, like if you're using GPT-4 and 3, that would be a really good place to use it, because you wouldn't need to do a lot of training for this. Enhanced question and answering. Now, the use case that I went over is some similarities to this, because it was a kind of a question answering type of thing that we built. Now this here starts with a relation entity extractor. So use the large language model to extract the entities. As we already know, for that, BERT might be a good choice. And then you use the knowledge graph. Now, what I would say with this is, if you remember when we were going through the use case, I might be able to say that Neil Armstrong is an entity, and born in is a relation based on analyzing the text. But I don't know from that whether internally in my business knowledge base, I'm using the same terminology. So that alignment issue of external versus internal terminology is not addressed by this, but I just wanted to note that. So here they say, well, we need to extract entities, yes, but those entities, this assumes that the user is articulating the exact same entities that exist in the knowledge graph. And then in the last step, they have something called answer reasoner, which is what we were using as well, saying, okay, here's the response, articulate the answer from the response. And so for that part of it, GPT-3 is really great, and GPT-4, for a summarization task like that. So enhanced embedding. Okay, this picture is wrong. I have not updated this, but yeah, I will update it before I put the slides out. In a way, we have touched upon this in some of the previous methods. It is basically, if I'm building a knowledge graph embedding, let's say I'm using one of those graph neural networks, and now I have emails and text data that's tied to this, I can encode the text data as well, and then merge the two embeddings to get a more informed embedding that has both the graph information in it as well as the information from the emails. Like, for instance, I was giving you earlier the example of an email where, like maybe there's an email about a sale being closed that, I might want to know about. And, that way, that knowledge would be something you could extract. So let's move on. So I knew that I wouldn't have time to dig into this deeper. There is a third bucket called synergized LLMs and knowledge graphs. So we had one method that we discussed where there was a joint reasoning capability. Now, that particular method wouldn't fit into this bucket. When they say synergized, what they mean is that there's a common knowledge representation and that there's a common way of doing reasoning. So within the literature survey, they provide examples of this. I encourage you to dig into it. Again, I will add the reference to that. This kind of concludes, I think, my slides. So at the end, what I'd like to say is that if you kind of look through this, you're going to see knowledge graphs and large language models do complement each other. You do have some levers to decide how much you want to rely on the large language model, how much how much hallucination you want to allow for, because with the very simple use case that we walk through, 0 hallucinations, and so that's possible, but it comes at a cost. And so if you look at some of the larger organizations out there, like we were mentioning, Baidu and like some of the other ones, they have these types of models in production. Now, what makes this a bit more difficult to basically reuse, if you will, is these types of models. Like you can train a text model on a bunch of text, and then it's applicable suddenly to a whole lot of things, because that is shared knowledge that everybody might find useful. Like if I want to do sentiment analysis, I just continue training on my own data and I leverage what was trained before. Now, with the knowledge graphs, the challenge is, well, everybody's knowledge graph is going to be different. And so the structures are going to be different. The entities, the relationships are going to be different. So it isn't a space where OpenAI could come in and say, oh, we're going to create this unified model for knowledge graphs, and you can then fine-tune that. So I'd say that's the reason why these models are being used in production, even those that can hallucinate, but they're not necessarily put out in the open, because these tend to be efforts that are custom to the knowledge at hand. So if there are open source sort of knowledge graphs for common sense things, you will find models that have been tuned against that. But for your own business, it means you need to do this fusion. And it's not something you will be able to get off the shelf. And the thing is, when you do the fusion, then you don't really have a guarantee that the hallucinations will not happen, but you can use the knowledge graph as a guardrail. So if it's fused and I know that I want to adhere to the knowledge graph, if the large language model is starting to produce things that makes no sense, then you can validate against the knowledge graph. So you have some added guardrails you can use. In my opinion, businesses would be well advised to come up with a strategy of how to organize knowledge internally. You may not believe me, you may not believe in knowledge graphs. You don't have to, but you should believe in knowledge. You should believe in the value of knowledge and the value of data. And I think that's really important. It's a prerequisite, not just for what we've discussed here for large language models, but to be able to be more data-driven, to be able to leverage your data for analytics, and also to create a foundation for your AI endeavors. So that would be my big piece of advice. Thank you everybody for attending, and my apologies for all the sound issues during the live event. I hope I will be able to upload a version of this that does not have any of those issues. Thank you.